There is a line of volcanic islands in the Western Pacific, the Mariana Arc. 4 of them are inhabited: Guam, Saipan, Tinian, Rota. Together they hold 170,000 people. They are American citizens. They carry the same passports. They pay into the same federal programs. But there is no bridge to the mainland. No highway to higher ground. When the planet decides to move against these islands, nobody leaves. That is not a hypothetical. Right now, the strongest storm on Earth is centered directly over the same ocean that holds the deepest trench on Earth. The storm is moving northwest. The trench sits beneath it. And the people on those islands have nowhere to go. This is not a weather story with a geology footnote. It is a story about 2 planetary systems, the atmosphere and the lithosphere, active at the same time over the same geography. And the scientific frameworks we use to understand risk were never designed to handle both at once. Let us begin with what we can measure. The storm is Super Typhoon Sinlaku. At the time of its peak intensification, sustained winds exceeded 157 miles per hour. That places it at Category 5 on the Saffir-Simpson scale. The central pressure dropped below 900 millibars, a value so low that the column of air above the eye weighs less than 90% of what it would weigh under standard sea level conditions. That drop in pressure is not a number. It is a physical force. The ocean surface rises toward that low pressure. The atmosphere pulls water upward, and the resulting storm surge does not respect property lines or evacuation zones. What makes this storm unusual is not only its intensity, it is its timing. April is not typhoon season. The Western Pacific Basin follows a well-documented seasonal rhythm. Activity builds through late spring, peaks in late summer and early autumn, then fades. The historical average for named storms in April is less than 1 per year, a fraction of a storm. A Category 5 in April is a statistical outlier so far from the mean that it forces a question. What changed in the ocean to make this possible? The answer begins below the surface. The Western Pacific Warm Pool is one of the most thermally energetic bodies of water on the planet. It stretches from the Philippines eastward past Papua New Guinea and into the equatorial Pacific. And surface temperatures here are consistently above 28 degrees Celsius. But surface temperature is only part of the story. The more relevant measure is ocean heat content. How deep does the warm layer extend? How much energy is stored in the water column beneath the storm? In a normal tropical cyclone, the storm churns the ocean. Deeper, cooler water rises to the surface. That upwelling starves the storm of its heat source. It is a built-in, self-limiting mechanism. But when the warm layer is thick enough, when ocean heat content is anomalously high, that mechanism weakens. The storm churns, but the water that rises is still warm. The fuel supply does not cut off. The storm continues to intensify. That is what happened here. The warm layer beneath Sinlaku was deeper than the historical baseline for April. The ocean had stored heat during a previous El Niño phase, and that heat did not dissipate. It remained in the water column, carried by subsurface Kelvin waves, moving west to east across the Pacific. When Sinlaku passed over that stored heat, the ocean did not push back. It fed the storm. So, the atmosphere received a Category 5 in April, because the ocean had been accumulating energy for months. That is the first system. The second system is geological. The Mariana Trench sits directly beneath the same ocean. It is the deepest point on Earth's surface, nearly 11,000 meters below sea level. The trench exists because the Pacific Plate is subducting beneath the Philippine Sea Plate. The Pacific Plate is old. 150 to 170 million years old. Old oceanic crust is cold. Cold crust is dense. Dense crust plunges steeply into the mantle. That steep subduction angle produces one of the most seismically active zones on the planet. Within hours of Sinlaku's upgrade to Category 5, the United States Geological Survey recorded a magnitude 5.0 earthquake near Pagan Island. Pagan is part of the same volcanic arc, same trench, same subduction zone. The earthquake occurred at a depth of 226 kilometers, deep within the subducting slab. That depth matters. A deep earthquake of this magnitude does not produce strong surface shaking. It does not generate tsunamis. In isolation, it would be recorded, catalogued, and forgotten. But it is not in isolation. It is occurring in the same window of time, beneath the same islands, while the strongest storm on Earth approaches from the east. Two systems, one geography. No planning framework designed for the overlap. This is the setup. The storm is the strongest on Earth. The trench is the deepest on Earth. The islands sit exactly where these two extremes converge, and the people on those islands have no way out. The escalation is not a single event. It is a convergence. And to understand the scale of what is converging, we have to separate the systems before we bring them back together. Start with the storm's intensification timeline. 4 days before the upgrade, Sinlaku did not exist as a named system. There was a broad area of disturbed weather, a loose cluster of thunderstorms drifting west-northwest across the equatorial Pacific. Satellite loops showed disorganized convection. Forecast models gave it a low probability of significant development. That is normal for April. The atmosphere in early spring is not structured to support tropical cyclones. Vertical wind shear is often too high. Upper-level outflow is not well aligned. The monsoon trough, which acts as a spawning ground for storms later in the year, is not yet active. But something broke the normal pattern. The monsoon trough was more active than climatology predicted. Low-level convergence was stronger than average, and the ocean was not just warm. It was deep warm. Ocean heat content in the region where Sinlaku formed was in the 95th percentile for April. That means that in 100 Aprils, only 5 have seen this much stored heat in the water column. The storm organized rapidly. Within 24 hours, it went from a tropical depression to a tropical storm. The circulation tightened. Convection wrapped around the center. By the end of the second day, it was a typhoon. Then the acceleration began. Rapid intensification is defined as an increase in sustained wind speed of at least 30 knots over 24 hours. Sinlaku crossed that threshold once. Then again, in some 12-hour windows, the intensification rate exceeded what most operational models could capture. The central pressure dropped faster than the forecast guidance anticipated. The eye contracted. As the eye shrinks, the rotational speed increases. The same physics as a spinning ice skater, pulling in their arms. By the time the storm entered the Mariana region, it had intensified from a tropical depression to a Category 5 in roughly 96 hours. That is not a record, but it is near the upper bound of what the Western Pacific has produced in April. And the speed of that intensification has consequences for the people in the path. Warning systems are calibrated to historical rates of change. Forecast products are issued at regular intervals. Public messaging escalates in steps. When a storm intensifies faster than the historical norm, the public can fall behind. People may still be operating under yesterday's advisory, while today's storm is already a different category. This gap between the storm's reality and public perception is not a perception, a fall of force thing. It is a failure of the human timescale to keep pace with the planetary one. The storm's track also matters. Sinlaku did not stall, it did not meander, it moved with consistent forward velocity along a northwest trajectory. A stalling storm would have churned the same patch of ocean, drawing up cooler water from below, weakening itself before landfall. That did not happen. The steering pattern, a subtropical ridge to the north, held steady. The storm maintained its forward motion. It arrived at the islands near its peak intensity, not in a post-peak decay phase. That is the atmospheric escalation. Now add the geological layer. The magnitude 5.0 earthquake near Pagan Island occurred at 226 kilometers depth. That depth places it within the descending Pacific slab. The slab is cold and brittle. It does not deform plastically the way warmer mantle material does. Instead, it accumulates stress over long time periods, then releases that stress through earthquakes. The Wadati-Benioff zone, the plane of seismicity that traces the subducting slab, is active in this region continuously. Magnitude 4 and 5 events happen weekly. Magnitude 6 events happen every few years, so the earthquake itself is not statistically unusual. What is unusual is its timing relative to the storm. Here is the physical question that emerges from that timing. Does seismic activity at depth change the stability of the overlying volcanic arc? The answer is not straightforward. Deep slab earthquakes do not produce strong surface shaking. The energy attenuates over 226 kilometers of rock. The ground motion at the surface from a magnitude 5 at that depth is far less than from a magnitude 5 at 10 kilometers. In most cases, the shaking is barely perceptible. But perceptibility is not the same as consequence. The question is not whether people feel the earthquake. The question is whether the seismic waves, even at reduced amplitude, can influence slope stability on volcanic islands that are about to receive Category 5 rainfall. Volcanic islands are not stable platforms. They are constructed from alternating layers of lava flows, pyroclastic deposits, and hydrothermally altered rock. Pyroclastic material is loose. It does not have the cohesive strength of solid basalt. Hydrothermal alteration weakens rock by changing its mineral structure. Water circulating through volcanic systems converts primary minerals into clays. Clays have low shear strength. They become slippery when wet. The slopes of the Mariana Islands are composed of this heterogeneous material. In dry conditions, many of these slopes are stable. But when water enters the system, when rainfall saturates the volcanic soil and infiltrates into the fractured rock below, the effective friction holding the slope together decreases. Pore water pressure pushes against the grains. The slope approaches a failure threshold. Seismic shaking, even weak shaking, adds dynamic stress. The ground moves back and forth. That cyclic loading can push a slope that is already near its threshold over the edge. The combination of saturation and shaking is more destabilizing than either process alone. That is the escalation. Not a single dramatic trigger, a stacking of stresses. The strongest storm on Earth arriving at peak intensity. A seismic system active in the same window. The physical vulnerability, a volcanic terrain, and 170,000 people with no evacuation route. The systems are not interacting in the sense that one causes the other. They are interacting in the sense that their effects overlap in time and space. And that overlap, the simple fact of simultaneity over the same geography, is what existing risk frameworks were not designed to handle. The scientific tension in these situations is not between competing theories about what will happen next. It is more fundamental than that. It is between two different ways of understanding planetary risk. Single hazard thinking and compound hazard reality. Single hazard thinking is the dominant model. It assumes that disasters can be categorized. A hurricane plan optimizes for hurricane variables. An earthquake plan optimizes for seismic variables. The two frameworks do not speak to each other because the historical record of their overlap has been sparse. Emergency managers train for one primary event at a time. Building codes are written for one load case at a time. Risk assessments calculate probabilities for individual hazards, then treat those probabilities as independent. But independence is an assumption, not a law of nature. Compound hazard research is a relatively young field. It emerged from the recognition that real-world disasters often involve multiple hazards occurring simultaneously or in close succession. A typhoon followed by an earthquake, a volcanic eruption during a monsoon, a heat wave amplifying the effects of a drought. In each case, the total impact is greater than the sum of the individual impacts. Nonlinear amplification. 1 + 1 = 3. The mechanism of nonlinear amplification varies by context. Sometimes the interaction is physical. Rainfall from a storm saturates soil, making it more susceptible to landslide, triggering from an earthquake. Sometimes the interaction is infrastructural. A storm damages buildings, reducing their ability to withstand seismic loading. Sometimes the interaction is operational. Emergency responders sheltering from a typhoon cannot respond to a geological event until the storm passes. All three of these mechanisms are relevant to the Mariana situation. Let us examine the physical interaction first. The volcanic slopes of the Mariana Arc are composed of material with a specific property. It is sensitive to water content. Dry volcaniclastic deposits can maintain relatively steep slopes. But as water content increases, the material's shear strength decreases. The relationship is not linear. At a certain saturation threshold, strength drops off sharply. The slope becomes critically unstable. A Category 5 typhoon delivers rainfall at rates that can be several inches per hour. Over a period of 12 to 24 hours, total accumulations can reach 2 to 3 feet. That water does not all run off. A significant fraction infiltrates. It moves through fractures in the volcanic rock. It raises the groundwater table. It increases pore pressure throughout the slope. At the same time, the storm drives waves at the coastline. 30-foot seas pound the base of coastal cliffs. The wave action removes material that was providing lateral support. It undercuts slopes from below. A slope that might have been stable under rainfall alone becomes less stable when its toe is eroded. Now introduce the seismic layer. The magnitude 5. 0 earthquake at depth produces ground motion. The amplitude is small, the duration is short, but the frequency content of the seismic waves matters. Lower frequencies travel more efficiently through rock and saturated soil. They can induce a cyclic loading that reduces the soil's effective strength, even when the peak acceleration is modest. There is a known phenomenon in geotechnical engineering called cyclic mobility. It occurs when a saturated granular material is subjected to repeated loading. The pore pressure builds incrementally with each cycle. Eventually, the effective stress drops to 0. The material liquefies. It behaves like a fluid. This process is usually associated with strong, shallow earthquakes. But the threshold for cyclic mobility is not fixed. It depends on the initial density of the material, its saturation state, and the number of loading cycles. A weaker earthquake with the right frequency content and sufficient duration can trigger liquefaction in materials that are already close to their failure threshold. We do not know whether the Mariana slopes will experience liquefaction during this event. The data does not exist to make that prediction. but the physical possibility is real. And the scientific tension is that our models for predicting slope failure are calibrated to single hazard conditions. They assume either rainfall or shaking, not both. The compound case is understudied. Now consider the infrastructural interaction. The built environment on Guam and the other islands includes structures built to different codes at different times. Guam adopted modern building codes after Typhoon Pongsona in 2002, but not all structures have been retrofitted. Some buildings predate the code. Some have been damaged by previous storms and not fully repaired. The effective resilience of the building stock is not uniform. Wind loading and seismic loading place different demands on a structure. Wind loads are lateral and variable. They push on the building envelope. Seismic loads are inertial. The ground moves, and the building's mass resists that motion. A structure designed for wind may not have the ductility required for seismic loading. A structure damaged by wind may have lost some of its lateral capacity before the seismic event even begins. In a compound scenario, the order matters. If the typhoon arrives first, it damages the building stock. Weakened structures then face potential seismic loading. If the seismic event comes first, it may create cracks and other vulnerabilities that rainfall then exploits. The outcome depends on the sequence. Operational interaction is the third layer. Emergency response on Guam is organized around single hazard assumptions. During a typhoon, responders shelter in place. They do not move. Moving in a Category 5 storm is how responders become victims. The response capability is effectively frozen during the peak of the storm. If a significant geological event occurs during that frozen window, if a landslide blocks a road or a building collapses, the response must wait. The storm takes priority. The secondary event cannot receive attention until the primary event subsides. The delay could be hours or days. In that delay, lives could be lost. The scientific tension, then, is not a mystery, it is a gap. Our knowledge of individual hazards is deep. Our knowledge of compound hazards is shallow. The Mariana situation is exposing that gap in real time. The strongest storm on Earth is bearing down on a seismically active volcanic arc, and the frameworks we have for understanding what happens next were not built for this combination. This is where the tension lives. Not in dramatic uncertainty, in quiet, structural inadequacy. We have excellent models for the storm. We have excellent models for the earthquake. We have almost no models for what happens when both are true at the same time. The human consequences of this convergence begin with a simple fact. The 170,000 people on these islands cannot leave. There are no evacuation routes, no bridges to the mainland, no highway system to higher ground. The airport on Guam will close before the storm arrives. The ports will become unusable. The only options are shelter in place or shelter in a better place on the same island. That is the physical constraint. The human consequences flow from it. Sheltering in place during a Category 5 typhoon means different things depending on where you live. In a reinforced concrete building with impact-resistant windows and a secondary power source, survival is probable. In a wood frame house with corrugated metal roofing, survival is not guaranteed. Guam has a mix of building types. The northern part of the island has newer construction, much of it built to post-Pongsona codes. The southern part has older homes, some of them generations old, not designed for Category 5 winds. Typhoon Mawar in 2023 provided a recent stress test. Mawar was a powerful storm. It made landfall as a Category 4. It caused an estimated $3.3 billion in damage. Power outages affected nearly the entire island. Some areas remained without electricity for months. Water systems failed when treatment plants lost power. Roads were blocked by landslides and debris. The recovery timeline extended well beyond a year. Sinlaku is a Category 5. The difference between Category 4 and Category 5 is not incremental. It is exponential. Wind loads increase with the square of wind speed. 157 mile/hour wind exerts about 40% more force than 130 mile/hour wind. That difference translates directly into structural damage. Roofs that survived Mawar may not survive Sinlaku. Windows that held may shatter. Power poles that remain standing may fall. The human consequence of structural failure is displacement. People whose homes become uninhabitable must go somewhere else. On an island, the somewhere else is limited. Shelters will fill. Schools and community centres will be pressed into service. Families will double up. The displaced population will remain displaced for months. Water is the next layer. The island's water system depends on electricity. Pumps move water from wells to storage tanks. Treatment plants use electrical power to filter and disinfect. When the grid fails, backup generators activate. But generators have limited fuel. Fuel storage on Guam is finite. Refueling requires port access. The port will be damaged. The supply chain for fuel will be interrupted. Without water pressure, the system cannot maintain sanitation. Toilets do not flush. Washing is impossible. Waterborne diseases become a risk. After Mawar, some residents were without running water for weeks. The health consequences of that interruption were measurable. Increased cases of gastrointestinal illness, skin infections, and other conditions associated with poor sanitation. Medical infrastructure is the third layer. Guam Memorial Hospital is the island's civilian acute care facility. It has some hardening, it has backup generators, but its capacity is limited. The hospital has roughly 200 beds. During a major disaster, demand far exceeds that number. Trauma cases from storm-related injuries. Patients with chronic conditions whose home care has been disrupted. People who need dialysis, oxygen, or other life-sustaining treatments that require electricity. When the grid fails, hospitals fall back on generators. Generators need fuel. Fuel needs delivery. Delivery needs passable roads and functioning ports. If any link in that chain breaks, the hospital's ability to provide care breaks with it. The population of Guam includes vulnerable groups. Elderly residents who cannot evacuate quickly. People with disabilities who require ongoing support. Infants who need clean water for formula. The very young, the very old, and the chronically ill are always the most vulnerable in any disaster. On an island with no evacuation route, their vulnerability is absolute. Now add the geological layer. The earthquake itself, at magnitude 5.0 and 226 kilometers depth, will not cause direct harm. The shaking will be minimal. No tsunami will be generated. The immediate human impact of the earthquake is negligible, but the indirect impact is what matters. The earthquake is a signal. It tells us that the subduction zone is active, not unusually active. The background seismicity of the Mariana arc is always present, but active nonetheless. And activity at depth means that the stress state of the system is not static. It is in motion. The human consequence of that motion is not a single event. It is a distribution of possibilities. Most of those possibilities involve nothing more than the normal seismic background. But some possibilities involve interactions with the storm. A landslide triggered by rainfall on a slope that has been subtly weakened by seismic shaking. A road blocked by debris that would have remained stable if only one hazard had occurred. a building collapse that happens because the structure survived the wind, but not the combination of wind and ground motion. These are low probability events. But low probability events occur, and when they occur on an island with no evacuation route, the consequences are concentrated. There is no margin for error. The 170,000 people cannot spread out. They cannot leave. They absorb the full impact of whatever happens next. The political dimension of these human consequences also matters. The residents of Guam and the Northern Mariana Islands are American citizens. They serve in the US military at rates higher than most states. But they cannot vote for president. They have no voting representation in the Senate. Their representative in the House is a non-voting delegate. When federal decisions are made about disaster funding, response prioritization, and recovery resources, the political weight of 170,000 territorial residents is less than the political weight of 170,000 people in a state. That structural disadvantage has real consequences. After Typhoon Mawar, the federal response was criticized as slower and smaller than what a comparable mainland event would have received. The criticism was specific and substantiated. The recovery took longer than it should have. The gap between federal support and actual need was visible. Sinlaku will test that gap again. A Category 5 storm plus an active subduction zone. The human consequences will depend not only on the physical intensity of the events, but on the speed and scale of the response. And the speed and scale of the response depend, in part, on political representation that the Marianas do not have. That is the human consequence. Not a single catastrophe, a cascade of constraints. No exit, fragile infrastructure. Limited medical capacity. A response system that has historically under-prioritized territorial Americans. And two planetary systems converging at the same time, over the same islands. Cascading effects are what happen when the consequences of one system failure trigger failures in other systems. The initial hazard does not have to be the largest hazard. It just has to be the one that breaks the first link in the chain. In the Mariana situation, the first broken link is the power grid. The electrical system on Guam is vulnerable to wind. Transmission lines are above ground. Poles are designed to withstand certain wind loads, but Category 5 loads exceed the design threshold for most of the system. When lines come down, power stops. That is not a failure. It is an expected outcome. The grid is not engineered to survive a direct hit from a Category 5 typhoon. No grid is. The cascades begin the moment the grid goes down. First, water. The island's water supply depends on electric pumps. Without power, the pumps stop. Water pressure drops. Storage tanks drain. Within hours, residents lose access to running water. Hospitals switch to backup generators. The generators keep the pumps running, but only as long as fuel lasts. Fuel supplies are limited. Refueling depends on roads and ports. Second, sanitation. Wastewater treatment plants also require power. When they lose power, untreated sewage can back up or overflow. In a densely populated area with damaged infrastructure, sewage overflows create immediate public health risks. Bacterial contamination, viral transmission. The conditions that allow outbreaks of waterborne disease. Third, medical care. Hospitals have generators, but generators do not power every system. HVAC may be limited. Refrigeration for medications may be intermittent. Oxygen concentrators may fail. Patients on dialysis require specialized equipment that is not always backed up. The hospital becomes a site of triage, not a site of comprehensive care. Fourth, communication. Cell towers have backup batteries, but batteries last hours, not days. When the batteries drain, the network goes down. No phone calls, no internet. No way for residents to receive updates or request help. The emergency broadcast system may continue operating on backup power, but without cell service or electricity, many people cannot receive the signal. Fifth, transportation. Roads become impassable. Fallen trees, downed power lines, landslides, and flooding block major routes. The airport closes. The port is damaged. The island becomes isolated not only from the mainland but from itself. Emergency vehicles cannot reach some neighbourhoods. Medical evacuation becomes impossible. These cascades are predictable. They happened after Mawar. They will happen again after Sinlaku. The question is how much worse they become when a geological event overlays the storm. Now introduce seismic activity. The magnitude 5. 0 at depth is not strong enough to cause widespread damage on its own. But it does not need to be. It only needs to add stress to systems that are already stressed. Consider the roads. A typhoon saturates the soil and erodes the bases of slopes. A slope that is already close to failure requires only a small additional trigger. A seismic wave, even a weak one, adds dynamic loading. The slope fails, the road is blocked. The block is not the result of the typhoon alone or the earthquake alone. It is the result of both. Consider the buildings. A structure that has been damaged by wind loading may have lost some of its structural integrity. Cracks in walls, distorted frames, weakened connections. When ground motion occurs, even modest motion, the weakened structure may fail. Not because the earthquake was strong, because the typhoon prepared the building to fail. Consider the response. Emergency personnel are sheltering during the storm. They cannot assess damage until the winds drop. If a geological event occurs during that window, the response is delayed. A person who could have been rescued within an hour must wait 12 hours. The difference between 1 hour and 12 hours can be the difference between life and death. These are the cascading effects. They are not dramatic. They are not cinematic. They are logistical. A blocked road here, a delayed response there. A hospital generator that runs out of fuel because the resupply ship is stuck outside a damaged port. A water system that takes weeks to restore instead of days. The cumulative impact of these small cascades is larger than the sum of their parts. The recovery from Mawar took more than a year. The recovery from Sinlaku, with the added complexity of coincident seismic activity, could take longer. Every cascade adds time. Every added week of space placement increases the human toll. There is another cascade that is less visible, economic. Guam's economy depends on tourism and military spending. Both are disrupted by a major typhoon. Hotels close, flights are cancelled. The military repositions assets. The flow of money into the island stops. Residents who live paycheck to paycheck run out of money. Businesses that were already marginal close permanently. The economic recovery trails the infrastructure recovery by months or years. The people most affected are the ones with the fewest resources. Low-income households, renters, people whose homes were not built to modern codes, people who cannot afford to evacuate to a hotel on the mainland, even if evacuation were possible. The cascading effects of a compound disaster are regressive. They fall hardest on those who are least able to bear them. The final cascade is psychological. Displacement is traumatic. Losing your home, your community, your sense of safety. Living in a shelter for weeks or months. Not knowing when the power will come back. Not knowing when your children can return to school. These stresses accumulate. They produce measurable increases in anxiety, depression, and post-traumatic stress. The mental health consequences of a major disaster often outlast the physical recovery. In a compound scenario, the psychological burden is higher. The uncertainty is greater. The sense of being at the mercy of multiple planetary systems, the storm above, the ground below, can be overwhelming. That is not a weakness. It is a normal human response to abnormal conditions. The cascading effects of the Mariana convergence are not a single catastrophe. They are a network of failures, each triggering the next. Power to water, to sanitation to health, roads to response to rescue, economy to livelihood, to mental health. The network is dense. The connections are many. And the trigger, the strongest storm on Earth plus an active subduction zone, is already in motion. Future projections in a compound hazard scenario are not predictions. They are explorations of possibility. The scientific basis for projection is weaker than for single hazard forecasting because the historical record of compound events is sparse. But the absence of data is not the absence of risk. It is an indication that we need to think carefully about what might happen, even if we cannot assign precise probabilities. Let us project forward along 3 dimensions: the geological, the climatological, and the infrastructural. First, the geological dimension. The Mariana subduction zone will continue to produce earthquakes. That is not speculation. It is a statement about the long-term behavior of the system. The Pacific plate will keep subducting beneath the Philippine Sea plate. Stress will accumulate and release. The frequency of magnitude 4 and 5 events will remain high. The frequency of magnitude 6 and 7 events will be lower but non-zero. What is less certain is the potential for a larger event, magnitude 7.5 or above, on the megathrust interface. The scientific literature on this question is not settled. Some researchers argue that the steep subduction angle and the old, cold nature of the slab produce low coupling between the plates. Low coupling means the plates slide past each other more freely, accumulating less stress at the interface. Large megathrust earthquakes would be less likely. Other researchers argue that the coupling estimates are uncertain. The paleoseismic record for the Mariana system is sparse. The instrument record is short. We simply do not have enough data to say with confidence what the maximum possible earthquake is in this system. The range of plausible projections is wide. From a repeat of the moderate background seismicity the region has experienced historically, to a larger event that the historical record has not yet captured. Projecting forward means acknowledging that range, not narrowing it artificially, not dramatizing the worst case, holding the uncertainty openly. Second, the climatological dimension. The ocean is warming. The Western Pacific warm pool is expanding. Ocean heat content is increasing. These are measured facts. Their effect on tropical cyclone behavior is the subject of active research, but some conclusions are robust. Warmer oceans provide more energy for storms. Storms that form in a warmer world have the potential to intensify more rapidly and reach higher peak intensities than storms in a cooler world. The April anomaly. A Category 5 typhoon in what used to be the off-season may be a signal. It may be a low probability event that happened to occur, or it may be the leading edge of a shift in the climatological baseline. The data does not yet allow us to distinguish between these possibilities, but the direction of the trend is clear. The conditions that produced Sinlaku, high ocean heat content, a more active monsoon trough, favourable upper-level outflow, are becoming more common. They may become the new normal. If that is the case, then the Mariana Islands face a future with more frequent off-season major typhoons. The window for preparation and recovery will compress. The historical rhythm of typhoon season, which allowed for seasonal cycles of repair and reinforcement, will no longer hold. Third, the infrastructural dimension. Guam and the other islands will need to adapt. The adaptation will be expensive. The cost of hardening the power grid to withstand Category 5 winds is measured in billions of dollars. The cost of retrofitting older buildings is similar. The cost of building seawater barriers and improving drainage is additional. Federal funding for territorial infrastructure is limited. The political representation gap means that the Marianas must compete for resources with 50 states, each with its own congressional delegation. In a world of increasing compound hazards, that competition will intensify. The islands that are most exposed to the convergence of atmospheric and geological extremes are also the islands with the least political power, more, to demand protective investment. There is a projection that is not often stated explicitly. The exposure gap will widen. Communities with political power will invest in resilience. Communities without political power will remain vulnerable. When the next compound event occurs, and there will be a next compound event, the consequences will be distributed unequally. Now project forward to a specific scenario, not a prediction, a possibility, a future April. Ocean heat content is higher than it is today. A tropical disturbance forms east of the Marianas. It intensifies rapidly. Within 96 hours, it is a Category 5. Its track is similar to Sinlaku's. The islands are in the direct path. At the same time, the subduction zone is in an active phase. The background seismicity is elevated. A magnitude 5.5 earthquake occurs at moderate depth beneath the arc. Not strong enough to cause damage on its own, but strong enough to stress the volcanic slopes. The storm arrives. Rainfall saturates the ground. The groundwater table rises. Pore pressure increases. The slopes approach their failure threshold. Then the seismic waves arrive. Not from a single earthquake, from a cluster of them. The ground shakes repeatedly over a period of hours. The cyclic loading pushes saturated slopes over the edge. Multiple landslides occur simultaneously in different parts of the island chain. The power grid fails. The water system fails. The roads are blocked. The port is damaged. The response is delayed because emergency personnel are sheltering from the storm. The combination of wind damage and landslide damage exceeds the capacity of the local response. Federal assistance is requested. But federal resources are stretched thin because other parts of the country are also experiencing extreme weather. The response is slower than anyone wants. The recovery takes years. This is a projection. It is not a prediction. It is a plausible outcome given the trends we are observing. The question is not whether this exact sequence will occur. The question is whether our planning frameworks are adequate for a world in which such sequences are possible. They are not. Not yet. The future projections from the Mariana convergence point to a single conclusion. We need to stop thinking about hazards in isolation. The strongest storm on Earth and the deepest trench on Earth are not separate stories. They are the same story. The story of a planet where systems overlap, where boundaries are permeable, where the atmosphere and the lithosphere speak to each other over inhabited ground. That story is not over. It is just beginning. Let us return to where we started. The strongest storm on Earth is locked onto a target. 170,000 people. No mainland, no highway out. 4 islands. 30-foot seas. A Category 5 typhoon that has their exact coordinates. That alone would be a story. But while meteorologists were issuing an upgrade to the storm, something else was registering on a completely different set of instruments. A magnitude 5-point earthquake. directly beneath the same island chain, in the same window of time. Two systems, two sets of data, one geography. When two systems are active over the same ground at the same time, you are no longer dealing with a weather event. You are dealing with something we do not have a name for yet. Not because the science is missing, because the frameworks are missing. Our language for describing planetary risk has not caught up to the reality of planetary behaviour. The Mariana Islands sit at the intersection of two extremes. The deepest trench on Earth, the warmest pool of water on Earth. The trench produces subduction and seismicity. The warm pool produces storms. The islands are caught between them. This is not a coincidence in any mystical sense. It is a coincidence in the mathematical sense. Two independent processes, atmospheric and geological, have converged in time and space. The probability of that convergence is low. But low probability is not zero probability. And when low probability meets high consequence, the result is a risk that deserves attention. The attention has been uneven. The storm has received coverage. The earthquake has received less. The compound interaction has received almost none. That is not a failure of individual journalists or scientists. It is a structural feature of how we organise knowledge. Atmospheric science and geology are separate disciplines, separate conferences, separate journals, separate funding streams. The compound space between them belongs to no one. That space is where the most important questions live. What happens to saturated volcanic slopes under seismic loading? What happens to wind-damaged buildings when the ground shakes? What happens to emergency response when two hazards demand attention at the same time? These questions are not being asked systematically because the institutional structures to ask them do not exist. The Mariana convergence is a test, not a test of the planet. The planet is simply doing what it does. The Pacific plate subducts. The ocean stores heat. The atmosphere generates storms. These processes are ancient. They have been operating for millions of years. The test is of us, of our ability to see systems whole, to move beyond single hazard thinking, to build frameworks that can handle the overlap. 170,000 people are about to experience that overlap directly. They will ride out the strongest storm on Earth. They will feel the ground move beneath them. Meaning, they will live through the aftermath. And they will do all of this without the luxury of abstraction. For them, the convergence is not a scientific problem. It is a Tuesday night. What they deserve is not speculation. It is attention. Clear-eyed, system-level, consequence-aware attention. The kind of attention that asks what happens when the deepest trench and the strongest storm occupy the same coordinates. The kind of attention that admits uncertainty without using it as an excuse for inaction. The kind of attention that builds better frameworks for the next convergence because there will be a next convergence. The planet is not done moving. The storms will keep coming. The ground will keep shaking. The ocean will keep warming. The question is not whether the planet will change. It will. The question is whether we will learn to see it whole. The strongest storm on Earth. The deepest trench on Earth. 170,000 people in between. That is the frame. Not catastrophe. Not apocalypse. A signal. A measurable, documentable signal that the separation we have built between atmospheric and geological risk is a human construct, not a natural boundary. The planet does not respect our categories. It never has. Our job is to catch up